Welcome to the lesson on dynamic arrays. In Chapter 2, we learned about arrays. Arrays are fast, but they have one problem. Their size is fixed. In this lesson, we build an array that can grow. We will see how it grows, why doubling is the smart way to grow, and how to write it safely in C. Let's start with a simple question. Why do we need dynamic arrays at all? The next few slides show the problem with a fixed size array and lead us to the fix. By the end of this lesson, you can do 5 things. Let's look at them one by one. First, you can tell size and capacity apart. Size is how many elements you use right now. Capacity is how many slots you have room for. You always keep size between 0 and capacity. Second, you can add an element at the end in fast time. You write into a spare slot. You only grow the buffer when it fills up. Third, you can grow the array safely in C. You call the realloc function with a temporary pointer before you change the data pointer. Fourth, you can explain why doubling gives big O of 1 on average. The rare big copy is spread over many cheap adds. Fifth, you can avoid the common C bugs. Things like losing your memory block, leaks, and mixing up size and capacity. One idea drives this whole lesson. Keep a buffer that is bigger than you need. Add into the spare slots cheaply. Double the buffer when it fills. Then spread the rare copy over many cheap adds. Here is the path we take through dynamic arrays. First, what a dynamic array is. An array that can grow when it fills up. Then how it sits in memory, with its size and its capacity. Next, append the common case, which is fast on average. Then the growth rule, and why doubling the size is better than adding one slot at a time. Here is the second half of the path. After the growth rule comes access, insert, and delete, and what each one costs. Then the invariants, the things that must always stay true. And last, the common mistakes to avoid. Let's carry the pain from Chapter 2. We keep adding until the array is full. Here the array holds 4 elements and it has room for 4, so size equals capacity. The array is full. The next add has nowhere to go. Look at the code. We make an array A with 4 ints. We also make a pointer B and ask malloc for 4 ints. Both hold exactly 4 ints. Neither block can grow by itself. This is the trap. A C array does not grow on its own. If you write to it at index 4, that slot does not exist. This is undefined behavior and it is a bug. To grow, we ask for a bigger block. Its address may stay the same or it may change. The real question is, how much bigger? The first idea is simple. We start when the array is full. Size equals capacity, so there is no free slot. So we make a new block. It has room for one more element, that is size plus 1. Then we copy all the old elements into the new block. Then we write the one new value at the end. This works and it is simple, but it copies every element on every single add. Now try to predict. You build a list from empty. You add one item at a time, grow by 1. When the list holds n items, how many element copies did you do in total? A small hint before the answer. When you add the kth item, you first copy the k minus 1 items already there, so the counts stack up. We add them on the next slide. Now let's see why grow by 1 is slow. When you add item number k, you first copy the k minus 1 items already there. Let's build the list and keep a running total of the copies. The first add. The list is empty, so you copy 0 items. The running total is 0. The second add. One item is already there, so you copy 1. The running total is now 1. The third add. You copy 2 items. The running total climbs to 3. The fourth add. You copy 3 items. The running total is now 6. The fifth add. You copy 4 items. The running total reaches 10. You can see it. Each add copies more than the one before, so the total grows fast. Jump ahead to the nth add. It copies n-1 items. The running total is n times n-1 divided by 2. Now add them all up. 0 plus 1 plus 2 and so on up to n-1. The total is about n squared over 2 copies just to build the list. This cost is called quadratic. Let's feel this number. Say you build a list of 1 million elements this way. You copy about 500 billion elements. That is half a trillion copies just to place 1 million, and it gets worse fast. 10 times the items means 100 times the copying. There must be a better way. Now the fix. We change one rule. When the array is full, we grow to twice the capacity. We double it instead of adding 1. This row is the old rule, grow by 1. It resizes on every add. The total copying is about n squared over 2. Each add copies the current size, so the per add cost is theta of n slow. This row is the new rule, doubling. It resizes only after full sizes 1, 2, 4, 8, and so on, so resizes are rare. The total copying stays under 2n, that is big, O of 1 per add on average. A single resize add is still big O of n, but they are rare. So doubling turns a big O of n squared build into a big O of n build. Each add costs big O of 1 on average. That relief is the whole point of this lesson. Let's name the idea. A dynamic array is a backing buffer plus spare room. The growth rule is double when full. Cheap adds right into the spare room. Rare resizes copy the live elements.